Hi, we're going to do a little bit of a tricky linear equation problem that's in lesson 5. But before we can do the trickier parts of it, we're going to do the easier parts of it. And to do that, to review that, I'm going to review some linear equation stuff. First of all, this, hopefully you can see that. Let's see. Let me try this. Oh, sorry, kitten. This involves distance equals rate times time. In linear equations, this should look something like y equals mx plus b. We won't worry about plus b. It'll come in later, don't worry. But t is our x variable, t is time, d is distance, that's our y variable, and m, which always stands for rate, is the r variable, stands for r, rate. But let me just go over with, now that you've been studying nonlinear functions, let's just talk about linear functions. If you have an x and a y, and you have, let's say, y equals 5x, right? 0, 5 times 0 is 0. 1, 5 times 1 is 5. 2, 5 times 2 is 10. 3, 5 times 3 is 15, right? So what we're saying is every time x comes up a notch, we add 5. That's all it means. Linear equations just mean that. Every time x comes up a notch, add 5. This 5 to 10 is 5, 10 to 15 is 5, right? So linear equations just, and it looks like multiplication. Why? Why does it look like multiplication if I'm telling you you would just repeatedly add? Because the way we write repeatedly add, repeat addition, the way we write that is multiplication. So if I wanted, for example, if I want you to add 2 plus 2 plus 2, I'm probably not going to say that. I'm probably going to say 3 times 2. 3 added, 2 added 3 times. Okay? So when you see linear equations, please don't freak, because it's just saying for every unit you go up on the x axis, you add on the y-axis the same amount. So you go x and then 2, 3, 4, 5, x, 1, 2, 3, 4, 5, and you'll end up getting a straight line, more or less. Right? If you have the same ratio, it'll cause you to have these similar triangles that stack up, and you'll get a line. Okay, I know that sounds complicated, similar triangles that stack up, but basically it just means that the little triangle that's 5 by 1 is similar to the next triangle that's 10 by 2, right? Those are just blow-ups of each other into the same proportion. Okay, now the next thing I want to review before we do this problem, which is a little bit of a pain, is if I have a rate of 1/4 mile, and I can do that in 6 minutes, right? 1/4 mile, 6 minutes. I have a couple of choices for how to express this rate because this is a fraction, so that's awkward, right? So what if I multiply both of these by 4? That means 1 mile in 24 minutes. That still doesn't resolve the question of how I'm going to express the unit. I either am going to do 1 mile in 24 minutes or 24 minutes in 1 mile. Those are the same thing. Those are equivalent. I mean, you can tell me that, right? If I tell you 1 mile in 24 minutes versus 24 minutes in 1 mile, right? You can tell me those are the same thing. We put it one way or the other depending on what's coming next. If what's coming next has minutes on the top, and I want to get rid of them, then I'll use this one with minutes on the bottom. Okay, let's get to this problem. I'm not going to write it on the board because it's really long, but I'm going to ask you to go to your teacher's guide thingy that your mom has, and it's called Consider This Story, Lesson 5. May, June, and July were running at the track. May started first and ran at a steady pace of 1 mile for every 11 minutes. All right, let me write this down. May went 1 mile for every 11 minutes. Now, they expressed it as 1 mile for every 11 minutes, and I'm going to trust them that they need it in that form, 1 over 11 and not 11 over 1. I'm going to trust them that they expressed the unit that way because that's ultimately how they need it, but 11 minutes per 1 mile is also fine too. I'm going to trust that they wrote it this way because later we're going to need it that way. So in order to do this problem, we have another concept to go over, and that's when there's different people leaving at different times or starting at different times. So on the top of this problem, I'm going to put time 0. We're going to measure everyone according to May's time, right? So time 0 is when May starts, okay? May started first and ran at a steady pace of 1 mile every 11 minutes. June started 5 minutes later. So at 5 minutes, June started. June. Okay? 5 minutes. July started 2 minutes later. So at the 7-minute, that's not proportional, but at the 7-minute mark, July started. Right? But July had two different laps. July went like flat out and then slowed down. So she had 2 different laps, 2 different pieces of her race. First, we have to figure out how long the first one was. And then the last one was, she maintained the steady pace 3 more laps and slowed down to 1. Okay, so let me just go over everybody again one more time. May and June were running at the track. May started first and ran at a steady pace of 1 mile every 11 minutes. So I'm just going to write May. Her distance will equal 1 mile over 11 minutes times the amount of time she runs, right? Time is going to be minutes on the top, so we'll cancel there. Then it says June starts 5 minutes later. So the way we do this in algebra, we say she runs 1 mile every 9 minutes, so that's 1/9 times t minus 5. Now, why do I say t minus 5 instead of t plus 5? It's because she runs 5 less minutes than May runs. So her time running is less because she leaves later. She's having orange juice and coffee. I'm sure it's a croissant. 1 second. Sorry, I had to take a phone call. Anyway, this t minus 5 is because for 5 minutes, and this is June, so she's my namesake, so I know this for a fact, she's eating chocolate croissants, right? For sure. While May is running. I know this. So her time of running is 5 minutes less. We're going to make t May's time and t minus 5 June's time. Okay, here comes the tricky part. We have to do some messing around with July. Excuse me. July has these two parts, okay? So I'm just gonna steal this part of the board. July started 2 minutes after June and ran at a steady pace, running 1/4 of a mile in 1.5 minutes. Now you notice the other one said 1 mile in 9 minutes. This says 1/4 of a mile in 1.5 minutes. We just have to multiply everything by 4 to get the rate. I don't know why they did that, just to make your life hard, I think. So 1/4 times 4 is 4/4. That's 1. 1.5 times 4 is 6. And now we have our rate. So for July, we know her rate for the first part, there's gonna be 2 parts, okay? For the first part is gonna be 1/6, 1 mile in 6 minutes, okay? She maintains this pace for 3 more laps. Now here's another place that they make your life difficult. They don't tell you how long that takes, so we have to figure that out. First of all, we're told that 1 lap is 1/4 mile. And they give us her original, oh, I see, maybe they weren't trying to make your life difficult. They give us her original speed in 1/4 mile is 1.5 minutes. Okay. So they say that her initial, she has 2 laps. It's going to be D equals 1/6T, but minus 7 this time. Minus 7, but here comes the tricky part. Let me make this a little bit more. T minus 7 because it's 2 more minutes that she was idle than June, who was 5 more minutes idle than May, right? So 1/6, but the answer key tells us that this first lap goes to minute 13. So we've got to figure out, how do we know this was 6 minutes? It went from 7 minutes to 13 minutes. How do we know that? Well, it's because, let's see, she did this for 3 laps. 3 laps. And each lap takes her 1.5 minutes. So 1.5 plus 1.5 plus 1.5 is 4.5. Let's see, I have notes. 1 second. 1 second. This is where I got stuck last time. She runs 6 minutes. Now, how did I figure out she runs 6 minutes? I figured out she ran 6 minutes. All right, let's do it again. July started 2 minutes after June, which we figured out, but put -7 there. Because -5 + 2 -7, right? And ran at a steady pace. Oh, I see how it is. She ran the first quarter mile in 1.5, and then she did 3 more, right? So it's not 4.5, it's another 1.5, which makes it 6 minutes. Now I understand. So it's 4. They write it like it's 3 laps, but it's 4 laps. So it's 4 laps in 6 minutes. This is 6 minutes. This makes this the 13 mark, right? So the answer key tells us that it's 4t less than 13 or equal to 13. All that means is that her time for this first lap ends here. Okay, now we have the second one. In this period of time where she runs for 6 minutes, she writes minutes, for 6 minutes, how many miles did she run? Well, we know she runs 6-minute mile. So if she ran for 6 minutes, she ran for a mile. So I'm going to take over this part of the board again. So the teacher guide gives us her second part as, let's see, what am I trying to sort out? Okay, she maintained this steady pace for 3 more laps and then slowed down to 1 lap every 3 minutes. 1 lap every 3 minutes. 1 lap is 1/4 of a mile. Again, we're going to multiply everything by 4. So that's 1 mile in 12 minutes. So this second part is going to be d equals 1/12 t. Now this is important. -13, we figured out where we got the 13 from, plus 1. Well, that's the part I was struggling with. Was in this first run, she did 4 laps, 1/4 of a mile each lap. That's 4/4 of a mile, 4 miles. 4 times 1/4 of a mile, that's a mile. So we add this 1 because distance is what we're adding up. We add this 1 for her first lap. This is very complicated, but I hope this small video gets you started, and we'll talk about it if you need to talk about it more. All right, take care. Oh, wait, this is a couple. I'm going to do a part. Maybe I'll just continue instead of doing a part 2. They asked some questions. We have our equations, right, which I'm going to put on the top of the board now and answer our questions. May is distance equals 111 t, which is 1 mile and 11 minutes. June is distance equals 1 mile and 9 minutes times t minus 5. And July has 2 pieces. Piece 1 is distance equals 1/6 t minus 7. where t is under 13 or equal to 13. And the second piece is 1/12 t minus 13 plus 1 for t is greater than 13. All right, those are our equations. Hopefully you can see those okay. And then they ask, who's the first person to run 3 miles? Who's the first person to run 3 miles? So how would we figure this out? We want to figure out what t is at 3 for each of these. This is going to be added. So we just put in 3 and compare the times. Sorry. Then they said, did June and July pass May on the track, and if they did, at what mileage? Well, I'll go over on a second video, but maybe you can play with that on your own now that you have the equations and you understand where the equations come from. Because this is getting to be a little bit long, but I'll do a part 2 of this video for all the questions, because part of it is you have to, if you look, you have to graph. And I don't know with a whiteboard how I'm going to do that, but I'll figure it out in time for part 2. All right, take care, you guys.